Hello everybody, and welcome back to another Engineering Statics lecture video. In this video we are going to get to the fun stuff, which is trusses. In the previous videos I kind of teased you guys. I said, we're going to get to the fun, but we have to learn a couple things first. And those things were support reactions as well as distributed loads. But we've done that now, we're ready to go, we can actually jump into the fun. Now, why is this so much fun? Well, again, the stuff we're going to start learning in this video and beyond are actually going to be applicable to real-life design scenarios. The first half of this course with forces and moments, that was more just about mastering what is a force and what is a moment. Now we are going to take what we learned and apply them to actual everyday situations. Now in this video we're going to be covering trusses, and everyone here has seen a truss, I guarantee it. No way you stumble upon this video and have not seen a truss before. So you guys have all seen trusses, you guys know that it is a real life application, and what we're going to learn today in this video actually applies to real life. So it's great for us because we can start taking all of those skills that we've learned and apply them to realistic scenarios. Now before we begin, I just want to say that I hope you guys are all doing well, hope you guys are happy. I know it's hard to be happy at this time of year, especially in Canada, because it starts getting cold, and no one likes the cold. I know I personally, I'm not a big fan of the cold. Got a vacation house down in Phoenix. I love the heat. I love the heat, not a big fan of the cold, but hopefully you guys are doing well. Hopefully the heat stays on in your house. Alright, so with that being said, let's jump into trusses. Now trusses are very simple, and that's what makes them a very common design situation for things that you don't want to look pretty. For instance, if you guys look at a lot of the telephone poles, the really big ones, they're usually a collection of trusses. And same thing with old railway bridges. Now, typically when I say trusses, you guys think of these old railway bridges that we used to have. So this is actually the bridge here in Edmonton. And behind the bridge in real life now today, well, not real life because this is of course real life, but modern day, the university is actually behind this bridge. So if you guys are at the University of Alberta, chances are you guys have now seen this bridge. It's been retrofitted so that it is now of course a road rather than a railway track. But again, it's nice to see these old bridges really stand out. Now these bridges as trusses are actually a collection of two things, members and joints. So if I were to kind of draw this in two dimensions and I have a truss, each truss consists of two things. So we're going to have members, and these are the long, slender pieces that go between what we call the joints. So we have members and we have joints. Now in this particular picture here, the truss members would be those long pieces of steel, and the joints would be those rivet connections where all the steel pieces kind of connect. Now, trusses can actually be classified as two different things. The first one is a plane truss, or a two-dimensional truss, where all the members act in the same plane. The best example is actually the truss above and the truss that I kind of drew using the PowerPoint clip art. Because if we look here, the truss is actually just two members that are side by side and the railroad is in between. But those two members all act in the same plane, those two trusses. Now, the second kind of truss is something what we call a space truss, and these are basically 3D trusses where the members act in multiple planes. So for those of you guys that like to go to parties, go to raves, you guys usually seen the stage set up with these kind of trusses. So there's an example over there. So that's a three-dimensional truss. These ones get a little bit more complex to analyze, but good thing for us in this course, we are going to be focused on the first type, which are plane trusses. So nice 2D trusses. All the questions you guys will receive will look something like the one on the top right, something like that, nice and easy. Now, when we solve truss systems, we are actually interested in two things. So that's going to be the goal of these next couple videos, determining two things in trusses. The first is the axial force, so this would be the magnitude. Is it 100 kilonewtons? Is it 200 kilonewtons? Or if you're American, is it 100 pounds or 200 pounds? And then the second thing, of course, is whether the force acts in tension or it acts in compression. So that's going to be important. Again, we want the magnitude, and if that magnitude is in tension or is it in compression. Because if we're designing for tension, it's actually going to be different than if we design for compression. Makes sense? Now, we go into the analysis of trusses, we have to actually do some kind of groundwork before we get into the actual fun. When we talk about the analysis of trusses, there's going to be two methods, and they're going to be discussed in the next two videos. That's the method of joints and the method of sections. Now, before we get into those, we actually have to state two assumptions that we're going to make. So both of these analysis methods that we discussed are going to rely on these two assumptions for simplicity. The first one is that all external loads act at the joints. All right, so if I have my nice truss structure like this, and it has some loads, well, we can see that two of these loads at the very top act at a joint, so these are considered valid. However, if we look at the load on the left, it does not act at a joint, so we actually would not consider this case. So there's the first one. All the loads that we deal with in this course, they always act at the joints of the truss. And as we're going to see, this is actually a very valid assumption. The second one is that all joints act as pin connections. You guys saying, Clayton, what exactly does this mean? Well, if I take my truss and I were to analyze one of these joints, as we can see, the joint basically acts as a dot and all the forces intersect at that dot. Now, if we remember, this is actually a case of particle equilibrium. So the key thing here is this joint provides no moment resistance, or if we were to look at a free body diagram, there's no moments. All right, so this is basically particle equilibrium with no moments. And now you guys are kind of thinking, that's why we learned particle equilibrium. I know a lot of you guys, when I teach it, you guys kind of say, this isn't really useful because realistically we have moments, but we can actually design to make sure that there are no moments. And when we actually do truss design in reality, we as engineers have to make sure that there is no moments on our truss. So the question becomes, all right, these are two assumptions, and I hate assumptions because they're not realistic. Well, it turns out that these two assumptions in reality are actually pretty true. So if we were to look at the first assumption where all our external loads act at the joints, as engineers, we actually design our truss bridges for this to be true. So remember that for a truss bridge, it's basically two planar trusses running parallel to each other, and the railroad or the bridge acts in between. Now this bridge or the railroad that acts in between on that nice flat plate, it is actually supported by beams underneath. And these beams, which I've now shown in green, we only connect them to the joints of our truss. You never see one of these beams connected to the middle of a member. So this, as engineers, we actually can make sure that this first assumption holds true. Now the second one is that the truss joints are designed to be concurrent. And this again is something as engineers we get a pick. So if we were to go look at any bridge that we want to, so here's the one here in Edmonton, we can see that, yes, our joints are designed to be concurrent, because if I were to draw some lines, they always intersect at that same point. So again, these are two assumptions we make, but as engineers, we can ensure that these assumptions actually hold true. So it's actually kind of cool. And that's the fun of design. As engineers, we can start to control things. Now, when it comes to trusses, some other groundwork we have to talk about is the idea of truss stability, as well as the forces inside of a truss. All right, so it's actually not going to be too bad. We've discussed before that trusses carry either tension or compression. Now, what exactly does this mean? Well, it means that when we cut a truss member, we have to replace it with a single axial force. And this is nothing new. This is something that we did back in particle equilibrium. Remember, if we made a free body diagram and we cut through a rope or a cable, we had to replace that with an axial force. So it's going to be the same thing here. So let's say that we have our truss structure, and for some reason I'm very interested in this left-hand side. Now notice that the box that I create cuts through three of the members. So if I were to draw a free body diagram of this, I have to label all the forces on it. So we see that we have no external loads, which is not true in reality, but we can add them if we want to. But we know that we have a pin at the very left-hand side, so we have two pin reactions. And since I cut through three of the members, I can actually replace these with three forces. And not can replace them, but more or less I have to replace them with three forces. So in this case, I would have F1, F2, as well as F3. Now, if you guys remember from equilibrium, three equations, three unknowns, we can actually start to solve for these forces. And this is going to be something that we do in the next video. So remember that we define the tension as positive and compression as negative. So remember before in particle equilibrium, I always said assume tension. This means that our force is pointing away from our joint. And if we do the math and we get our force as negative, well, it means that it's actually in compression. But if we do the math and we get our answer as positive, it means it's actually in tension, which is good. So this is something, again, we're going to discuss more in the next video, the analysis of these forces. The only thing I want you guys to take away right now is that when we cut a truss member, we replace it with an axial load. And you guys are thinking, Clayton, piece of cake. I already know that. Well, let's move on to something a little bit different, which you guys may not know, and this is the idea of truss stability. So not only do we have to design for strength, but we also have to make sure that when we design our truss, it is stable. Now you guys are saying, Clayton, what exactly does that mean? Well, it means that if we design our truss, it doesn't just fall down. Remember that all the connections here are pins, so they're not going to resist any moment. And this will be one of the examples that I show you guys where it becomes obvious what I mean when it's unstable. Now you're saying, Clayton, this sounds complex. How do we make sure that our truss is actually stable? Well, it's simple. We actually have one nice equation. We have 2n minus m, and we have three cases. The first case is that it's greater than 3. Second case, it's equal to 3. And the third case where it's less than 3. Now you guys are saying, what is n? What is m? Well, it's simple. N is the number of joints we have, and m is the number of members that we have. And when we look at these three cases, it's going to mean three different things. If it's less than 3, it means that our truss is stable, which is a good thing, but it's indeterminate. What does indeterminate mean? Well, it means that we can't calculate our truss forces using simple statics or equilibrium. We actually have to do some more advanced calculations. Think of it as more 4 unknowns, but only 3 equations, something like that. The second case, where it's equal to 3, this is stable as well as determinate. So this means that our truss is stable, which is good, and we can actually determine the forces using simple equilibrium. So this is going to be the case we're mostly focused on in this course. The third case, when it's greater than 3, means that our truss is unstable. Now you guys are looking at this and saying, Clayton, I can do the math, but I'm still having a hard time picturing what exactly is going on. So let's do a quick little example. Let's say that we have this truss right here. And again, remember that all of the connections act as pins. So if I were to place a force, a lateral force at the top of this truss, we know that since there's no moment resistance, this truss is just going to go, right? It's just going to fall over. It's going to provide no resistance. So we know intuitively that this truss is actually unstable. So if I were to do the math and say, all right, I have my sexy equation, 2n minus m. I look here and I say, okay, I have 4 joints, the 4 purple dots, and I have 4 members, the 4 red lines. So I go 2 times 4 minus 4, I get 4. And we know that this right here is greater than 3, so it falls into that third case where our truss is unstable. So the math backs up what we can visually see. Now the question becomes, okay, well, how do I make it stable? Well, if we look at our equation, 2n minus m, and we want our number lower, well, we have to increase m. We have to increase the number of members. So if we look at our truss, and now we add that additional member, we know that if I were to put that force P, it's not going to just simply fall over. It's going to provide resistance because we now have that diagonal strut. Well, does the math tell us that? Well, yes. If we look at 2n minus m, in this case, m went from 4 now to 5 because we added an additional member. From here, we get 3, which means that our truss is stable. And it is also determinate, meaning if I wanted to, I can solve this truss and all the forces using equilibrium. So you guys are saying, okay, I know stable, I know unstable. What about determinate? I'm still a little bit confused with that indeterminate determinate thing. Well, let's see what happens. So an indeterminate truss, we would add another member. So in this case, we would add another member like this. So we can see that it's definitely going to be stable. It has a lot of resistance because it now has a cross brace. And if we were to do the math, 2n minus m, well, we got 2 times 4, but this time minus 6. We have 6 members. So this is equal to 2, which is less than 3, so it's stable as well as indeterminate. So if we were to look here, we know it's stable, but we actually can't solve it using just our equilibrium equations. We have to get into a bit more advanced calculations that are actually involving the material properties of the truss itself. So it's something outside of this course. All you guys would need to know is that this is stable. Now you guys are saying, all right, Clayton, what about real life? Well, in real life, we like to have indeterminate things because indeterminate is basically backup to me. If I have one of my members that fail, well, take it away, we still have a stable truss. Now, if I had a stable but determinate member and one of the members failed, well, then I go into that unstable category. So I like to have indeterminate members because it provides us some sort of backup in case things go wrong. So that is the concept of stability. Now, the last thing that we're going to talk about before we get into the real fun stuff, I forgot to just mention that, of course, In this particular class, we are going to be focused on stable and determinant. Indeterminate wouldn't do anything, because if I give you guys a truss you guys can't solve, well, nobody gets anywhere really. So the last thing we're going to discuss are something called zero force members. Now this is the secret to all truss questions in the exams. No matter what university, this is going to be the secret right here, because zero force members allow us to take very complex looking trusses and simplify them, because there is two relationships that we can use to determine if a member in a truss is zero force, or basically it carries no load. So again, there's going to be two cases. The first one is if two members meet at a joint without any external load. Now, if this is the case, both of those members that meet at the joint are zero force. They carry no load. So if this was my case here, and I had my joint, which is the purple dot, and I had my two forces from the members, I can automatically conclude without any calculations that both of these are zero force, meaning that both F1 and F2 are equal to 0. Now you guys are looking at this and saying, all right, Clayton, it's easy, but how the hell did you determine that? Well, it's simple. The idea of equilibrium. So if I were to set my x-axis as parallel with F1 here, because you can do that. You guys can set the x-axis however you want, as long as they're perpendicular. So one thing that students always forget is that they always have it as horizontal and vertical. But if I wanted to, I can rotate it. It's completely fair game to rotate it. Now, if I were to do this, and I were to go summation of forces in the y direction, well, we can see that F1 has no component. It's perfectly in the x-axis. So my only component, of course, is going to be something times F2, or that something is just a factor. Now, if this is the case, and I want to uphold equilibrium, we know that this is equal to 0. So something times F2 equal to 0, well, the only way this is going to be possible is if F2 is equal to 0. And if F2 is equal to 0, then F1 must also be equal to 0. So there's the first case. The second case is if we have three members that meet at a joint, again with no external load, and two of the members are collinear, meaning that they're parallel with each other, and the third member is non-collinear. That third member is actually a zero force member. Now again, this is a bunch of word garbage. If you guys want to see what this looks like, it would look something like this. So notice how my two top members are parallel with each other, so they're collinear, and then I have a third member that is not collinear. If this is the case, then that third member is actually going to be zero force. And from there I can say that, all right, we have F1 and F2, and they're going to be equal to each other, but not 0. Well, this F3 is actually going to be equal to 0. And the proof for this one is just the same as before. If I were to go summation of forces in the y direction, well, my only force in the y direction is F3, so it must be equal to 0. Now you guys are saying, okay, Clayton, it's pretty easy to see these two cases, but what is the importance of this? Well, again, it helps simplify our questions. So if we identify and remove these zero force members, our truss questions actually become rather simple. Give me an example? No problem. This is a truss that I love to give to students as an assignment, because if we look at this truss, it's pretty gross. It has 11 members in this truss. Now, I always ask the students, give me every force in this truss. And they look at that and say, excuse me, Clayton? Every force? 11 forces? Are you kidding me? That's crazy. I don't want to do that. That's a lot of work. But the trick to this truss is it has a lot of zero force members. So if we were to look at our two cases, all we have to do to identify them is just go through each joint. So if I were to look at, and we have a force P at the end. So if I were to look at this joint over here, automatically it does not fall into two of the cases, because it's going to have support reactions due to the pin. Notice that both of these cases, there can't be any support reactions or external loads. So I can conclude that this joint right here, I can't do anything. This joint can't do anything. And this joint, I also can't do anything, because we have that external load at all three of these joints. Now, if I were to go to the other joints and kind of work my way through, not a lot actually happens. If I were to look at this joint, well, we have 4 members, so it doesn't fall into any case. If I look at this joint, I have 4 members, so again, it doesn't fall into any case. This joint, 4 members, no case. But when we look at this joint, we have 3 members. Now, if we look at case 2, it talks about 3 members. And it says that the only qualification that we need is that 2 of the members are collinear. And if we look here, those top 2 members, they're collinear. Therefore, that third member must be 0 force. So if we look at this, I can say that that member in there is going to be 0 force. Now you guys are saying, Clayton, we just went through all the joints and we just took out one member. How's that helping anything? Well, here's the trick to 0 force members. You have to do more than one pass. You can't just go through it once, identify what you can, and say, yep, that's it, that's all. Because if we were to look at these joints now that we took away a member, things start to change. For instance, if I were to look at this joint down below, which before had 4 members, so we couldn't do anything, well now after we took away that member that goes vertical, it now has 3 members. And if we look at case 2, it says that if 2 of the members are collinear, then the third one is 0 force. And if we were to look here, those 2 diagonal members, well, they're collinear. So in this case, we can say that because of case 2, this member is actually 0 force. And then the same thing now with this joint. Before it had 4 members, couldn't do anything, but now it has 3, and as we can see, the top 2 are collinear. So therefore, this joint is also equal to 0 force. And then hold on one second, if we go to this joint now, it now has 3 members, 2 of them are collinear, so this is actually going to be 0 force. So again, the trick here, we need to do multiple passes. You can't just go through it once, say you're done. You have to go through it once and then go through it twice, and every time you remove a member, you have to recheck all the joints. So if we look at this, it was 11 members before, but now we actually simplified it to the following. Now it still looks like it's 7 members, but remember that these members right here, from equilibrium, they're going to be equal to the same. If I look at the case 2 above, after I remove F3, well, we know that from horizontal equilibrium, F1 must be equal to F2. So what I highlighted there in blue, that's essentially just one member. And then the same thing with the diagonal one. So we basically took a case where we had 11 members we had to solve for, and now we only have to solve for 3. So this is, again, the beauty of 0 force members, is that it takes our very complex truss and simplifies it, which makes all of our calculations much easier. Now, if you guys wanted to, you guys can still solve for all 11 members, and the math will show you that those are all going to be 0 force. The math still works out. But again, the name of the game in finals and midterms and any exam is speed. Remember that Cars from Disney, I am speed. That's what you guys should be doing before the exam, is giving yourself that little pep talk. Because in exams, again, the #1 killer is that students don't finish on time. If I were to do 11 calculations, that's going to take up a lot of my time. If I were to do 3, well, it's probably still going to take a lot of time, but it's going to be a lot less than 11. So again, this particular lecture, I'm just showing you guys kind of the fundamentals of trusses. In the next 2 lectures, we are going to start discussing how do we solve for these forces inside of the truss. Again, there's going to be 2 methods we discuss, the method of joints as well as the method of sections. So again, that's going to be the next 2 videos. But that's it for this particular video. Again, just nice little fundamentals of trusses. I hope it, helped you guys, got you guys excited. I personally get excited once we start talking about these realistic engineering scenarios. I'm not a big fan of those imaginary engineering things. That's what the math department's for, is the imaginary stuff. In engineering, we like to do real life. So yeah, that's it for this video. Thank you guys so much for watching. I really appreciate it. I will see you guys in the next lecture video.